The scorching sun of Mongolia's Gobi Desert beat down mercilessly on the weathered rocks, as paleontologist Sarah Chen wiped the sweat from her brow for what felt like the 1,000th time that July morning in 2019. The temperature had already climbed past 40 degrees Celsius and the day's excavation had barely begun. What started as a routine survey of late Cretaceous deposits would soon become a moment that would fundamentally alter our understanding of prehistoric apex predators. As Chen's trained eyes scanned the ancient sediments, something unusual caught her attention, a distinctive glint in the weathered rock face that seemed different from the typical fossil fragments they'd been finding all season. That moment would mark the beginning of a scientific journey that would challenge everything we thought we knew about the diversity of large carnivorous dinosaurs in the final days of the Cretaceous period. The discovery began innocuously enough, a small piece of exposed bone, its surface bearing the distinctive preservation pattern that gets every paleontologist's heart racing. But as the team carefully removed the surrounding matrix, something extraordinary began to emerge. The bone wasn't isolated. It was part of a nearly complete skull, and one unlike anything previously documented in the fossil record. Initial measurements suggested a creature of massive proportions, yet its features defied easy classification within known theropod families. The skull, measuring 150 centimeters in length, displayed a unique combination of characteristics that would soon ignite fierce debates within the paleontological community. The preservation quality was exceptional, revealing fine details of bone texture and anatomical features that typically don't survive the fossilization process. What made this specimen particularly remarkable was the presence of unusual sensory structures preserved in the skull, deep nerve channels and highly specialized orbital features that suggested sensory capabilities far beyond what had been previously documented in large theropods. These features hinted at a predator with hunting abilities that would revolutionize our understanding of late Cretaceous ecosystems. As the excavation progressed, more questions emerged than answers. Why had this clearly successful predator never been found before? How had it evolved such specialized features? And perhaps most intriguingly, what role did it play in its ecosystem during the final days of the dinosaurs? The skull's unique morphology suggested a hunting strategy, unlike anything previously known from the late Cretaceous period, challenging long-held assumptions about predator diversity and ecological niches in prehistoric ecosystems. The team worked meticulously through the blistering heat, their excitement growing with each newly exposed bone. The specimen's location in the Gobi Desert's Nemegt Formation placed it at approximately 66 million years ago, right at the twilight of the dinosaur era. This timing raised even more compelling questions. How did this predator interact with other known species from this period? What could its existence tell us about the diversity of life just before the Great Extinction? The implications were staggering, suggesting that even after more than 2 centuries of dinosaur research, our understanding of prehistoric life remained far from complete. As the sun began to set on that fateful day, casting long shadows across the excavation site, Chen and her team realized they were standing at the threshold of a discovery that would rewrite textbooks and challenge long-held theories about predator evolution. The skull they had unearthed represented more than just a new species. It was evidence of an entirely unknown lineage of advanced theropod dinosaurs, one that had evolved remarkable adaptations for hunting in ways no other known predator had done before. Little did they know that this was just the beginning of a scientific mystery that would captivate researchers and dinosaur enthusiasts alike, leading to years of intense study, debate, and revelations about the complexity of prehistoric ecosystems. The implications of finding such a completely unknown predator in well-studied rocks raised profound questions about what other discoveries might still await in the Earth's ancient sediments. How many other remarkable creatures might have existed without leaving a trace in the fossil record? What does this tell us about the gaps in our understanding of prehistoric life? As the team carefully documented their initial findings, they couldn't help but wonder, what other secrets might this ancient predator reveal about the last days of the dinosaurs? The revelation of a new apex predator from the late Cretaceous period requires us to fundamentally reassess our understanding of prehistoric ecosystems. 66 million years ago, the region that would become the Gobi Desert presented a dramatically different environment from today's arid landscape. Environmental reconstructions based on sedimentological and paleobotanical evidence paint a picture of a diverse landscape where subtropical forests intermingled with open woodlands, crossed by meandering river systems that supported a rich diversity of life. Within this dynamic ecosystem, the newly discovered predator, temporarily designated as Phantoma giganteus, occupied a unique ecological niche that had never been documented before. Initial analyses of the skull and subsequently discovered postcranial elements revealed a creature that defied conventional classifications. Standing at an estimated height of 4 meters at the hip and measuring approximately 12 meters in length, the Phantoma represented a significant departure from known theropod body plans. What made this predator particularly remarkable was not just its size, but its suite of specialized adaptations that suggested highly refined hunting capabilities. Detailed microscopic analysis of the skull revealed an unprecedented array of sensory adaptations. The creature's brain cavity, preserved in exceptional detail, showed enlarged areas associated with visual processing, while the inner ear structure suggested exceptional balance and spatial awareness. Most intriguingly, the skull bore evidence of highly developed sensory organs around the snout region, similar in some ways to the pressure-sensitive organs found in modern crocodilians, but far more extensive and complex. The creature's dentition presented another puzzle for paleontologists. Unlike the thick bone-crushing teeth of Tyrannosaurus rex or the blade-like teeth of smaller dromaeosaurids, Phantoma's teeth showed a unique serration pattern and enamel structure that suggested a completely different approach to dispatching prey. Scanning electron microscopy revealed microscopic wear patterns indicating a hunting style that combined precision biting with powerful grip strength, allowing for a more efficient killing method than previously known among large theropods. Biomechanical analyses of the postcranial skeleton revealed further surprises. The forelimbs, far from being reduced as in many large theropods, showed evidence of powerful musculature and specialized articulation surfaces that suggested they played a crucial role in hunting. The question that plagued researchers was clear: what selective pressures had driven the evolution of such a unique combination of features? The answer seemed to lie in the creature's hunting strategy, which appeared to be unlike anything previously documented in the fossil record. Environmental data from the surrounding rock layers provided crucial context for understanding how Phantoma interacted with its ecosystem. Analysis of carbon isotopes in the sediments suggested a seasonal climate with distinct wet and dry periods, while fossil pollen and spores indicated a mosaic of different vegetation types. This environmental variety would have supported a diverse array of potential prey species, from medium-sized hadrosaurs to larger ceratopsians, offering Phantoma a wide range of hunting opportunities. The discovery forced paleontologists to reconsider what they thought they knew about predator diversity in the late Cretaceous. How many other specialized predators might have existed without leaving traces in the fossil record? What does the existence of Phantoma tell us about the complexity of prehistoric food webs? The implications extended beyond paleontology, challenging our understanding of how ecosystems can support multiple large predator species through niche differentiation. Studies of the rocks surrounding the fossil yielded additional insights into the creature's life and times. Trace fossils, including footprints and possible den sites, suggested that Phantoma may have exhibited complex social behaviors. The discovery of multiple individuals in close proximity raised intriguing possibilities about pack hunting or other forms of social interaction, adding another layer of complexity to our understanding of prehistoric predator behavior. The scientific community's response to the Phantoma discovery was immediate and intense, sparking what would become known as the Gobi predator controversy. The initial publication in Nature, detailing the discovery and preliminary analysis, triggered a cascade of debate and competing interpretations that would reshape our understanding of theropod evolution. The controversy centered not just on the creature's unique features, but on fundamental questions about convergent evolution, niche specialization, and the diversity of hunting strategies among late Cretaceous predators. Professor James Morrison of Cambridge University led the initial skeptical response, publishing a detailed critique that questioned the team's interpretation of the fossil material. His analysis suggested that rather than representing a new type of predator, the unusual features of Phantoma might be explained as extreme adaptations within already known theropod lineages. This sparked a heated exchange in the academic literature, with researchers from institutions worldwide weighing in with their own analyses and interpretations. The debate intensified when a team from Moscow's Paleontological Institute, led by Dr. Viktor Petrov, announced the discovery of similar fossils at a different Gobi Desert location. Their specimens, while fragmentary, seemed to share some of Fantoma's unique features but also displayed significant differences. This raised new questions about whether these creatures represented a single species or an entire clade of specialized predators that had somehow escaped detection in the fossil record until now. Detailed analysis of the bone microstructure revealed growth patterns unlike anything previously documented in theropod dinosaurs. The histological studies conducted at multiple institutions using cutting-edge imaging techniques showed evidence of rapid growth followed by periods of slower development, suggesting a complex life history strategy. This pattern raised intriguing questions about the creature's metabolism and activity levels, challenging traditional models of theropod physiology. The controversy took an unexpected turn when Dr. Sarah Chen's team announced the discovery of distinctive tooth marks on prey species fossils that matched Fantoma's unique dentition. These marks appeared on bones from both large and medium-sized herbivores, suggesting that these predators were capable of taking down a wide range of prey. The feeding traces showed a precision and consistency that indicated highly specialized hunting behavior, providing concrete evidence of how these animals interacted with their ecosystem. Advanced computer modeling of Fantoma's skull revealed stress patterns and bite force capabilities that defied conventional understanding of theropod feeding mechanics. The model suggested that these predators could generate enormous bite forces while maintaining remarkable precision in their jaw movements, a combination previously unknown among large carnivorous dinosaurs. This led to heated debates about the evolution of different predatory strategies and the potential for multiple successful approaches to large prey hunting in the late Cretaceous. The discussion expanded beyond paleontology into broader questions of evolutionary theory and ecosystem dynamics. How could such a specialized predator evolve and thrive without leaving more extensive fossil evidence? What does its existence tell us about the potential for undiscovered diversity in other prehistoric ecosystems? The implications challenged long-held assumptions about the completeness of our understanding of dinosaur diversity and evolution. New dating techniques applied to the rock layers containing Fantoma fossils placed them precisely within the final 500,000 years before the end Cretaceous extinction event. This timing raised profound questions about the diversity of large predators just before the mass extinction, and what role, if any, specialized hunters like Fantoma might have played in the ecosystem's ultimate collapse. The debate forced paleontologists to reconsider their models of late Cretaceous community structure and the factors that contributed to the extinction of the dinosaurs. As research continued, the academic community remained deeply divided over the interpretation of Fantoma's features and its place in theropod evolution. Each new discovery seemed to raise more questions than it answered, challenging researchers to develop new methods and approaches to understanding this enigmatic predator. The controversy highlighted how much remained unknown about the diversity of prehistoric life and the complexity of ancient ecosystems. The reconstruction of Fantoma's hunting behavior and physical capabilities marked a watershed moment in paleontological research, combining cutting-edge technology with traditional analytical methods to bring this ancient predator back to life. Computer simulations based on the exceptionally well-preserved skull and skeletal elements revealed a hunting strategy that revolutionized our understanding of prehistoric predator-prey dynamics. The creature's most remarkable feature, its highly developed sensory apparatus, suggested hunting capabilities that would have made it a formidable presence in late Cretaceous ecosystems. Biomechanical analysis revealed that Fantoma possessed a unique combination of speed, strength, and sensory acuity. Its elongated limb bones, reinforced with unusually thick cortical walls, suggested both power and agility, a combination rarely seen in theropods of comparable size. The creature's estimated running speed, based on detailed musculoskeletal reconstructions, indicated it could reach speeds of up to 40 kilometers per hour in short bursts, making it an effective ambush predator despite its considerable size. The predator's hunting strategy, reconstructed through multiple lines of evidence including tooth mark analysis, skeletal biomechanics, and environmental data, painted a picture of a sophisticated hunter that used its enhanced senses to track prey in conditions where other predators might have struggled. The enlarged olfactory bulbs and highly developed middle ear structure suggested exceptional sensory capabilities, while the unique arrangement of blood vessels and nerve channels in the snout region indicated the presence of specialized sensory organs that might have allowed it to detect prey through multiple sensory channels. Perhaps most remarkably, Evidence from the brain case endocast revealed enlarged optic lobes and highly developed visual processing centers, suggesting that Phantoma possessed exceptional visual capabilities, possibly including advanced depth perception and motion detection. This combination of sensory adaptations would have made it a lethal hunter in the diverse environments of the late Cretaceous Gobi region, capable of tracking and pursuing prey under a wide range of conditions. Detailed analysis of prey fossils found in association with Phantoma remains revealed a hunting strategy that targeted medium to large-sized herbivores, particularly hadrosaurs and smaller ceratopsians. The precision of the bite marks and the consistent positioning of attack points suggested a methodical hunting approach that maximized efficiency while minimizing risk to the predator. This evidence pointed to a highly refined hunting strategy that had evolved over millions of years of selective pressure. The discovery of multiple Phantoma specimens in close proximity, along with trace fossils suggesting coordinated movement patterns, raised the intriguing possibility of social behavior among these sophisticated predators. The implications of potential pack hunting behavior in such large, sensory-advanced theropods forced a fundamental reassessment of social complexity in prehistoric predators. Analysis of growth rings in the bones suggested a prolonged period of juvenile development, possibly indicating extended parental care and complex social learning. The creature's hunting adaptations extended beyond its sensory capabilities. The unique structure of its forelimbs, featuring reinforced muscle attachment points and specialized joint surfaces, suggested an ability to grapple with prey in ways previously unknown among large theropods. This combination of grasping ability and powerful bite force would have made Phantoma an exceptionally effective predator, capable of subduing large prey with a combination of strength and precision. Environmental reconstruction of its habitat revealed a complex landscape where Phantoma's unique adaptations would have provided significant advantages. The mixture of open areas and denser vegetation, combined with seasonal variations in climate and prey availability, would have favored a predator capable of adapting its hunting strategy to different conditions. Evidence suggested that Phantoma was equally effective hunting in both open terrain and more densely vegetated areas, making it a truly versatile apex predator. The integration of all these lines of evidence painted a picture of a predator that was far more sophisticated than anything previously known from the late Cretaceous. Its combination of sensory capabilities, physical adaptations, and possible social behavior suggested a level of hunting prowess that would have made it one of the most effective predators of its time. The existence of such a highly specialized hunter raised profound questions about the complexity of prehistoric ecosystems and the potential for yet undiscovered diversity among ancient predators. The implications of the Phantoma discovery continue to reverberate through the scientific community, challenging our fundamental understanding of prehistoric predator diversity and ecosystem complexity. The existence of such a highly specialized hunter, previously unknown despite extensive paleontological research in the Gobi region, forces us to confront the limitations of our knowledge about prehistoric life. What other remarkable creatures might still lie undiscovered in the Earth's rocky depths? How many other specialized predators might have existed without leaving traces in the fossil record we've found so far? The evolutionary significance of Phantoma extends far beyond its unique hunting adaptations. Its presence in the final stages of the Cretaceous period, mere hundreds of thousands of years before the Great Extinction event, raises profound questions about the diversity of life in this crucial period. The creature's sophisticated sensory adaptations and potential social behavior suggest levels of complexity in prehistoric ecosystems that we are only beginning to understand. These findings challenge the traditional view of dinosaur evolution as a simple progression toward ever larger or more specialized forms. The study of Phantoma has also revolutionized our understanding of predator-prey relationships in prehistoric ecosystems. The evidence of its hunting strategies, combined with its unique sensory capabilities, suggests that the arms race between predator and prey was far more sophisticated than previously imagined. The presence of such a highly adapted hunter implies equally sophisticated defensive strategies among its prey species, hinting at complex evolutionary relationships that we are only now beginning to unravel. Perhaps most intriguingly, the discovery raises questions about the role of specialized predators in ecosystem stability and their vulnerability to environmental change. The fact that Phantoma existed so close to the end Cretaceous extinction event prompts us to consider how specialized hunting strategies might have contributed to both the success and ultimate extinction of these remarkable creatures. What factors enabled such a sophisticated predator to evolve, and what ultimately led to its disappearance? The technological advances that enabled the detailed study of Phantoma have opened new avenues for paleontological research. The combination of traditional fossil analysis with cutting-edge imaging techniques, biomechanical modeling, and molecular studies has created a template for future investigations. These methods are already being applied to other fossil specimens, promising new insights into prehistoric life that were impossible just a few years ago. The controversy surrounding Phantoma's classification and evolution continues to drive new research and theoretical developments in paleontology. The debate has expanded beyond questions of taxonomy into broader discussions about convergent evolution, the development of specialized adaptations, and the nature of evolutionary innovation itself. How many times have similar adaptations evolved independently in response to similar environmental pressures? What does this tell us about the predictability of evolutionary outcomes? Looking ahead, the Phantoma discovery suggests that we may need to fundamentally reassess our understanding of prehistoric biodiversity. If such a large, specialized predator could remain unknown until now, what other surprises might await discovery? The finding challenges us to consider how many other remarkable creatures might have existed without leaving traces in the fossil record, and what this means for our understanding of prehistoric life. The ongoing research into Phantoma continues to yield new insights and raise new questions. Each answer seems to open doors to further mysteries, revealing the complexity of prehistoric ecosystems in ways that challenge our preconceptions. The discovery serves as a humbling reminder that despite centuries of scientific investigation, our understanding of Earth's prehistoric past remains incomplete. What other extraordinary creatures await discovery in the rocks beneath our feet? How many more chapters of Earth's prehistoric story remain to be told? As we continue to uncover new evidence and develop new techniques for studying prehistoric life, the story of Phantoma stands as a testament to the endless capacity of the natural world to surprise and amaze us. It reminds us that even in well-studied areas of science, groundbreaking discoveries are still possible, and that the greatest mysteries of Earth's past may still lie waiting to be revealed. What other remarkable creatures might we discover in the years to come, and how will they change our understanding of life's long journey through time?